This video represents part 4 in our series of discussions about applications of partial derivatives in thermodynamics. We'll start with the heat capacity ratio difference, Cp minus Cv. Remember our discussions in the past, we talked about the constant pressure heat capacity and the constant volume heat capacity, and how the constant pressure heat capacity always exceeds the constant volume heat capacity. That difference we'll find is much greater in gases than it is in liquids and solids, and we'll do some computations here in a few moments. The expression we have here actually shows an equation that was derived in the text, and time permitting I'll actually go through this derivation in a future video. But we'll start here with our discussion of this difference between the constant pressure and constant volume heat capacities. Now hopefully you do remember the definitions of beta, which is the expansion coefficient here and represents the change in volume that occurs when we change the temperature. Kappa, you may recall, also represents, and the compression factor represents the change in volume that occurs when we change the pressure under isothermal conditions. So we're talking about isothermal compression. So let's look at the values for an ideal gas, or this difference for an ideal gas. In the last video we actually derived beta, the expansion coefficient for an ideal gas, and that was equal to 1 over T. We also derived the expression for kappa for an ideal gas, which is 1 over V. So if we just plug these values into our expression here, we get PV over T, which of course is equal to NR based on the ideal gas law. And this gives us the relationship that Cp is equal to Cv plus Nr. Of course, you'll remember we actually mentioned this earlier in our discussion for an ideal gas, that the difference between the two was simply equal to N being the number of moles times the gas constant. But here we've actually used the mathematical derivation to show that that is indeed the case. Now, if we're looking at the molar values for the heat capacity, of course, N would be equal to 1, and the difference between Cp and Cv would just simply be equal to the gas constant, which would be 8.314 joules per Kelvin per mole. So let's take a look at the monatomic gas, which, if you'll recall from our earlier discussions, according to the equal partition theorem, the constant volume heat capacity for 1 mole is 3/2 times R, which means that R being 8.314, the constant volume heat capacity is 12.47 joules per Kelvin per mole. Compare that to the constant pressure heat capacity, which is 3/2 R, the constant volume heat capacity, plus R, as indicated above, which makes it 5/2 R, and that's 20.8 joules per Kelvin per mole. There's a significant difference in the case of the monatomic gas between the constant volume and constant pressure heat capacity. Now, let's take a look at a system with liquid. So we'll look at liquid water here. And in this case, again, we'll use the expression as on the previous slide. However, we do not have a simple theoretical way to determine the expansion coefficients and the isothermal compression factor, so we have to go to tabulated values. These are measured empirically. So we get the beta values and the kappa values indicated here that we'll use in our equation. And then if we're interested in molar quantities, we'll calculate here the difference in the molar heat capacities. We use the molar volume for water, which is a little over 18 milliliters per mole. And so then the difference in plugging all those numbers into the equation, the difference in the molar heat capacity, CPM minus CVM, is 0.487. Again, compare this to the case for the ideal gas for monatomic system. The difference was 8.314 joules per Kelvin per mole, and here for the liquid it's 0.487. So it's a much smaller difference in the case of condensed phases when compared to gases. When we go to tables, we'll generally find heat capacities listed for the constant pressure situation, simply because most of the experiments that we carry out are under conditions of constant pressure, and it's easier and more straightforward to measure. But here we see that the difference between the constant pressure and constant volume heat capacities is actually not significant. Perhaps significant is the wrong word here, but it's not a very large difference between the two, and that will be the case for all condensed phases. There's only a small difference between these heat capacities. We do have to be careful with units here for using these calculator to do these calculations as opposed to MathCAD, which handles the units itself. We have to be wary of the fact that in order to end up with SI units, meaning in order to end up with an answer in joules per Kelvin per mole, the kappa values have to be in inverse pascals, and the molar volume must be in cubic meters per mole. We'll note above the kappa value that's tabulated, that's given here, is actually an inverse bar. So we'll have to do a conversion from inverse bar to inverse pascals if we're doing this calculation on a calculator. Alright, so now we're going to go take a look at enthalpy. We had been concentrating in the previous videos on internal energy changes, and specifically you may recall that when we looked at changes in internal energy, we expressed our fundamental equation in terms of changes in volume and changes in temperature because it was most convenient to do it with those variables. In the case of enthalpy, we'll find that it's more convenient to express changes in terms of pressure and temperature, and so very similar way we write the equation, the differential equation for changes in enthalpy with respect to a derivative with respect to pressure under isothermal conditions and a derivative with respect to temperature under isobaric conditions, constant pressure conditions. This is very similar to what we did before with internal energy. We're just using pressure and temperature instead of volume and temperature. We'll recognize, of course, that the derivative with respect to temperature at constant pressure is just the constant pressure heat capacity as noted in a previous video, and we're left with this other term here, which is the derivative with respect to pressure under isothermal conditions. It is analogous to the internal pressure for the internal energy. If you'll recall, we had internal pressure for internal energy as being defined as derivative with respect to volume under constant temperature conditions. And we'll note that for an ideal gas, we stated that that was equal to 0 because this is a term that's based on interactions. So the internal pressure was equal to 0 for an ideal gas, as we discussed earlier. We'll also note that this derivative with respect to pressure for enthalpy is also equal to 0 for an ideal gas, again because it's related to interactions. In systems with no interactions, dH/dP at constant T is equal to 0. It's only the presence of interactions that causes it to take on a non-zero value. So just like internal pressure, this particular partial derivative is representative of interactions within our system. We'll also note, analogous to the internal pressure that we dealt with in earlier discussions, that the dH/dP at constant T is equal to negative Cp being the constant pressure heat capacity here, and this derivative of temperature with respect to pressure under conditions of constant H. Again, this is analogous to what we had derived for the internal pressure du dV at constant T, and so we had in that case the constant volume heat capacity, and we had the derivative with respect to volume. And so you'll see that there is a very straightforward connection here between these two, and the derivation of the equation for enthalpy is done in a very similar manner to that which is done for the internal pressure. So go back to the previous slide and prove to yourself that this is indeed correct. The point here is that this derivative that we're talking about, the temperature with respect to pressure, is something again that we can measure in the lab. If we set up an experiment with constant enthalpy so we have constant enthalpy, and we measure the temperature change, which occurs when we change the pressure, we'll be able to determine this derivative. So what we want to do then to determine, and then if we determine that derivative, then of course we can determine this dH dP at constant T, which again, remember, is representative of attractive interactions within the system. So here is such an experiment. In this situation, we start with gas on the left side here with initial pressures P1, V1, and T1, and there is a porous plug. On the other side of that is a piston that's right up against the plug. So there's no gas on the other side of this porous plug. And what we do is we push this piston on the left through so that we're pushing the gas through the porous plug and push it all the way through so that we have now all this gas on the other side at a pressure, temperature, and volume, and no gas on the left side. So we pushed all the gas through. So note what's happened here is that we have a situation where we have changed the pressure by pushing it through. The final pressure, the final volume, and the final temperature are all different from the initial pressure, volume, and temperature. Okay? For this process, it turns out that delta H is equal to 0. So it's a constant enthalpy process. We'll actually go through this derivation on the next slide just to prove it to you. And so if we can measure the temperature change that occurs in this process based on the pressure changes that are occurring, we can get this coefficient dt dP at constant H. All right, so let's take a look here very quickly at the derivation that's occurring here in this this particular apparatus, which is called a Joule-Thomson apparatus, by the way, and this is referred to as a Joule-Thomson expansion. The process, the apparatus is insulated, it's adiabatic, there's no heat transfer that occurs with the surroundings, so Q is equal to 0, and that of course means that if Q is equal to 0, delta U is just very simply equal to W. Well, let's take a look here. We can actually divide this process up into two steps. The first step involves pushing the gas from the left side through the porous plug, and the work associated with that, what we're going to refer to as W1, and then the gas pushes the piston on the right side, and that we'll refer to as W2. So the total work done is equal to the work associated with pushing the gas through the piston, through the porous plug on the left, and then the gas pushing back the piston after it passes through the porous plug on the right. So the total work is just the sum of these two. Now, in W1, we have that work is just very simply equal to what's on the left side of that particular apparatus on the previous slide, and so we'll note that the pressure remains constant throughout that push. So we start with an initial volume of V1, but since we're pushing the gas all the way through to 0 volume, the final volume is equal to 0. So the work associated with the process on the left is just P1V1. By the same token, on the right side, we have a situation where we have this pressure, negative P2 is the pressure of the gas, and it remains constant as it pushes back the piston. The initial volume, of course, is 0 because there's no gas there initially, and the volume is 0. As the gas pushes it back, the volume increases to a final volume of V2. And so on the right side, the work is negative P2V2. Okay? Now, therefore, if we take that work, the work associated is just the sum of those two, okay, and that's equal to delta U. Delta U is U2 minus U1. So U2, the internal energy in state 2, the final state, minus U1, the internal energy of the initial state, is equal to the work done, and that's just P1 V1 minus P2 V2. Well, we can now rearrange this equation. And so what we're going to do is we're going to take P2V2 and move it over to the left side of the equation, and take U1 and move it over to the right side of the equation. So we end up with U2 plus P2V2 is equal to U1 plus P1V1. Well, if we go back to our definition of enthalpy, we'll recognize, because enthalpy H is equal to U plus PV, U2 plus P2V2 is just H2. And U1 plus P1V1 is just H1. So what that means is that the initial enthalpy, which is H1, is equal to the final enthalpy, which is H2. So this is indeed a constant enthalpy process. So going back to the setup for the Joule-Thomson expansion, we've just shown that indeed this is delta H equal to 0. So that means that any temperature and pressure changes we make to figure out our partial derivative is under conditions of constant enthalpy. Now, we actually have a name for this partial derivative. You may recall that the derivative dT/dV under conditions of constant U that we talked about in previous videos, we called that the Joule coefficient. We actually have a name for this new partial derivative, dT/dP at constant H. This is referred to as mu JT, which is the Joule-Thomson coefficient. So here we have a graph for molecular nitrogen that shows the Joule-Thomson coefficient at different temperatures, temperature plotted along the vertical axis, and pressures. So you'll note in this region here in the darker blue where the Joule-Thomson coefficient is greater than 0, and this means that dT/dP at constant H is greater than 0 in that region. Now, if we consider an expansion where gas is expanding from a high pressure region to a low pressure region, that means because it's going from high to low, then delta P for that situation is less than 0. If delta P is less than 0 and the Joule-Thomson coefficient is greater than 0, then that means delta T must also be less than 0. Again, let's go back and state that again. If the Joule-Thomson coefficient is greater than 0, that means this derivative here is greater than 0. If delta P is less than 0, then dP is less than 0. And since the Joule-Thomson coefficient must be greater than 0, that means that delta T must be less than 0 as well. So when the Joule-Thomson coefficient is positive, we will note a temperature drop during expansion. Let me repeat that. When the Joule-Thomson coefficient is positive, the temperature will drop when the gas expands from a high pressure region to a low pressure region. So this entire region shaded here in the darker blue, if we find ourselves and if the nitrogen is at a temperature and pressure that falls within that region, we know that when it expands, its temperature will drop. Conversely, if the nitrogen gas is in a temperature and pressure region outside of that darker blue area, the Joule-Thomson coefficient is less than 0, and under those circumstances, we'll note that the temperature will increase when the gas expands. Some of you may have noted, as we talked about this during a recent experiment where we were releasing carbon dioxide gas into a cylinder, that the regulator on the CO2 tank got cold, and that was because in that particular temperature and pressure regime, the Joule-Thomson coefficient for carbon dioxide was greater than 0, and when the CO2 gas expanded from the high pressure region inside the tank to the low pressure region outside the tank, its temperature dropped significantly. And that's going to occur when attractive interactions are very strong. The stronger attractive interactions are going to cause a temperature drop during a particular expansion process. So again, just to repeat, if the Joule-Thomson coefficient is less than 0, the temperature will increase during expansion. And if the Joule-Thomson coefficient is greater than 0, the temperature will drop during an expansion, as indicated here. Here are just as a table of Joule-Thomson coefficient for various gases. You'll notice that hydrogen and helium, for example, have negative values for the Joule-Thomson coefficient. They are relatively small, but that means that they will tend to heat a little bit during expansion. On the other hand, we'll note that carbon dioxide, as we just mentioned, has a relatively large positive value, means that that will cool on expansion. And looking at methane, CH4 is also positive and it will cool on expansion. And that means we have strong attraction in those situations where it cools on expansion. Ammonia is even larger, 28.2. It's almost 3 times the factor, 3 times the value of the coefficient for carbon dioxide. So ammonia's attractive interactions are incredibly strong, and so we can explain that simply because there's hydrogen bonding in ammonia. We know it's going to have very strong interactions, so we do see that reflected in a very large Joule-Thomson coefficient. It's important to note, of course, that the Joule-Thomson coefficient is in fact temperature and pressure dependent, as indicated on the previous slide, and that the values here are specified at 273 Kelvin and 1 atmosphere. Now, Joule-Thomson cooling can be used as a refrigeration process. Just going through this particular diagram shows that we have a gas fed into a compressor, pressurizing it to high pressures and allowing it to pass through, as we see here in this particular device, pass through a chamber from a high pressure region and to expands here into a low pressure region, and that expansion results in significant cooling. If it cools enough, this is actually a process that can be used to liquefy gases. We might find some condensation into liquid. If it remains in the gas, then the remaining gas is fed back through the tube at the cooler temperature, and of course as it's fed back through, it exchanges heat with the gas coming through, so it actually helps to cool the gas coming out as the remnant gas passes back through. So this is a cyclic process. The remnant gas goes back into the compressor, is pressurized again, and continues to pass through. Every time it passes through, the temperature gets cooler and cooler until ultimately we do get liquid coming out of this refrigeration process. Of course, this will only work when the Joule-Thomson coefficient is greater than 0, because as you'll recall, as we just stated, the gas will cool on expansion if it's greater than 0. If it's less than 0, this will not work. So this finishes the fourth in our series of discussions about applications of partial derivatives in thermodynamic systems. I hope you enjoyed. Stay tuned for the next video.